Good morning, everyone. Thank you. Let's start. How are you doing today? Ready for the new class? All right, so my name is Arie, and I will be teaching that course for this semester, and eventually we hope to convert that course into online version of the course that will run almost by itself asynchronously. But this time, since this is a completely new course and we're offering that first time, I would like to have some feedback from you and more questions. If you do not understand something, you can stop me at any moment and we can talk about that because I need to adjust as well the level of exposure that I'm giving to that course. So keep in mind that you can ask any kind of questions. No questions are silly or anything like that. You're welcome to ask anything you feel appropriate. And if you don't understand something, you can stop me at any moment. All right? Yes.
Which time is it you're taking or teaching the course? Like second time, third time?
What do you mean? What time?
Which time is it that you're teaching the course? Like, is it been the second time, the third time, the fourth time you've been teaching this course?
This course is first time.
Oh, it's new.
It's completely new course.
Oh, okay.
Yeah, so this course will be part of the certificate, graduate certificate. It will be part of neuroengineering requirement course. It will be also electrical engineering graduate course, which will be in multiple different certificates. So it's course which will have very broad audience of people involved in this course. And this is why I need all of the feedback from different people on how it goes, because this will be essential to adjust the level of the course to a particular level that we want. Okay, that everyone will have something out of it. All right, I will talk today about syllabus. I will talk about other things. But first of all, a few words about myself and why I'm teaching that course. So my office is here on 5th floor, but most likely you will not find me in my office. I'm rarely there. I'm working all over the campus in different places, sometimes remotely. Best way to contact me is by email. And if you send email related to questions on that course, just add like EE 633 or 733, that I will see that this is about that course. Okay, just because I'm getting probably like 100 emails per day, that I will not miss your email. Just put in the title of the email that prefix, all right? So office hours will be after that lecture. Sometimes I will not have time. Sometimes, most of the times, hopefully I will have time for your questions after the lecture. If you have some issues staying after the lecture or before the lecture, we can always talk about other times when we can meet in the office, on Zoom, any way which is comfortable for you, all right? So just send me email. We can choose some day and time when we can meet and talk, all right? A few words about my original background, research background. Good morning. Please sign in. Where is the sign-in sheet?
Oh, sorry.
Return to me. Yeah, here. All right. All right, so my bachelor's degree thesis was on signal processing, voice activity detection. And if you can imagine what voice activity detectors are used for, typically they are used in phones. Zoom is using that, obviously. So it needs to mute you when you're not speaking. Okay, so if you're talking to the microphone and it's like overall noise, other things are happening around you, only when speech happens from your side, then you need to activate that voice activity detector. So it's binary decision on like whether you are speaking or not. Okay, it has also a lot of military applications, like if you have military vehicles which are very noisy and you're driving inside the tank or whatever it is, and you're talking through some analog system, amplifying all of the noises around. Clearly the operator cannot hear you. They cannot hear anything. So it looks more or less like that type of noisy thing. If you're looking at that like tiny signal, it may be difficult to see, but it's like all huge noise. So you need to clean that noise first to get that type of signal where you have more clear signals, and signal to noise ratio is much better. And then you can activate your voice activity detector when you have some sort of speech detected. So I used all kinds of spectral techniques, Burg estimator and other things to detect the things, to clean the things, and to activate it. And this was my bachelor's degree. And then my master's degree was on robust control, where I developed different techniques and methods for designing controllers for microjet, different theorems of stability of different linear systems, mainly, related to generalizing Nyquist theorem, if you're familiar with controls, and both the theorems. So you have, in my master's work, I have generalization of all of the theorems for any kind of neighborhoods and for other things, and for also uncertain systems, which is very important for actual control, because most of the time we don't really know the plant. We don't know the actual model. The model is kind of vague and uncertain. You have parameters which we don't really know, and they might also change in time. So you need to control it still. So you need all of these tools to do that. So frankly, this is the work that I'm proud the most out of all of the work that I've done so far in all of my years doing research on all kinds of things. And like, funny thing is that I want that theorem at the bottom and formula on my grave, okay? Like if somebody asks you what I want to be written on my grave, that formula at the bottom, okay? You can mention that. This is like the thing that I proved. It was differential topology theorem, which for some reason nobody else proved before me, which was like big thing for me, because this is something that I consider important. But most people don't care, right? Who cares about math? And this is my PhD. So my PhD was on visual tracking, different objects. It could be all kinds of contours. It could be crowds which are moving and finding all kinds of anomaly in crowd movements with optical flows of different kinds, or visual tracking of different objects in video sequences. So this was my PhD. And then I did also postdoc on biomedical image processing analysis and signals. And obviously my research interests somehow cluster around all of these topics, which are including computer vision, biomedical image processing analysis and signals, as well mathematical modeling of different kinds, robust control, and then also doing some machine learning. And project examples include all kinds of sequential Monte Carlo, which is particle filtering type of tracking algorithms, image signal-based biomarkers, where we have CTs or MRIs. We extract all kinds of features out of that, or signals that we extract different features and trying to correlate it to clinical outcomes, trying to use machine learning to get these outcomes somehow, or brain signal modeling. We have a lot of that kind of projects in neuroengineering, and deep learning-based prediction of vital signs, typically for babies. I'm working with pediatrics doctors and helping them to identify different things like bradycardia, apnea, and other issues with their breathing or heart rate based on vital signs, trying to predict it forward a few seconds, that they will be able to do some interventions with that. Here are a few examples of these projects where you have, for example, phoneme analysis from brain signals. You're recording from deep brain stimulator and ECOG strips on the surface of the brain. You record all kinds of brain signals. You're trying to identify what person is saying based on the vowels and other things that you segment in time. And you don't have, we have microphone recordings, but we do not use microphone recordings. This is only for ground truth type of idea. Like, can we identify when they speak and what they say? It's just like reading the brain from brain signals type of things, brain-computer interfaces problems, and how you tune deep brain stimulators for Parkinson's disease, how you explore all of the questions of epilepsy and finding seizure onset zones based on the signals that you record from the brain, like stereo EEG, things of that kind. And then you have at the top here, like here you have devices that we are developing, embedded devices which are measuring EKG and other things, trying to predict, using machine learning again, what happens to the heart rate in the future, or what happens to the respiratory rate in the future, to predict if they stop breathing. If babies, for example, stop breathing, you would like to know that ahead of time, that it's getting worse. And this is all of the work with lungs, airways, segmenting different things in images, and so on. So we have multiple different things going in the lab. And this is the thing that I like the most, magic. And I think that I picked that course because this course is magical in a sense. Math, for me, is kind of magic. And it's interesting that when I came to the United States, I taught courses in a completely different way. I started all of the courses with just starting first chapter in the topic, just writing formulas on the board, bringing all of that in, all of the material, giving tests and all of that. And then when instructors in the United States talk to each other, like how you need to teach the course, first thing that they say, you need to break the ice with students. Like first lecture should be like breaking ice with students. So the funny thing here is that why you need to break ice with students? To show them that you're human. This is the main theme. Like why are you showing that you're breaking ice? Like, you need to be human. So I'm clearly not human, so for me breaking ice is difficult. So I'm showing something which matters to me, all right? And the funny thing about that particular movie is that after that magic trick, I couldn't find that eraser for 2 days. Like, real story. Like, it disappeared and I couldn't find it. Like, I looked everywhere. Like, for real, I couldn't find it. Where did it go? So this is that funny thing, okay? So this is about me. Now, what about you? So if you can introduce yourself briefly and tell me what program you are in, what your interests are, and maybe something short and brief about you, which not many people know. No? So let's go like from left to right, from my left to right. Okay, Manuel?
I am Emmanuel. I am from optometry background. I'm an optometrist and I'm doing a PhD in vision science. So my work is we are trying to understand how we see, basically, and when we are losing our vision, we do not recognize that we are going blind unless we've lost at least 40% of our eye cells, which means the brain kind of amplify the signals from the eye. It's kind of feeling, missing, percepts. So in our lab, we do electrophysiological recording, and we try to make sense of those signals by modeling them, getting functions, and we also design stimulus to probe the visual system. So it involves a lot of functions and systems, and then because of my background, these things were too abstract to me. So when I came here to UAB, I reached out to Arie, and then we worked on some projects, and he trained me, and these things, some of these things started to make sense. So as I wanted a course to register to further deepen my knowledge, I saw this course, and then, right?
Guys, I'm Mohammed Al-Zubi. I was bachelor's in electrical here, and I'm doing master's in electrical here. I'm excited about learning about particle filters in this class, and something you may not know about me is I work at a library doing STEM camps for kids.
Hello everyone, my name is Sadia. I'm from Bangladesh. So I did my bachelor there, back there, and I did my bachelor in finance. So this is a big change for me to change the track. Now I am doing my master's here in electrical and computer engineering. So yeah, I hope I can cope up with everything. Thank you.
QC. Laura?
My name is Barl Risi. I got my bachelor's here in electrical and computer engineering. Now I'm doing my PhD in electrical engineering. Interested in computer vision, and I'm hoping to do my PhD in computer science and AI solution, knowledge solution.
My name is Neeraj. I'm from India. I'm doing my master's in electrical and computer engineering here, and My interests are just mostly currently I'm doing some research work with the medical people and applying machine learning on different medical problems. So like that's most of my work right now.
Okay.
My name is Hannah. I'm in the neuroengineering PhD program. And my work right now is mostly focused on Parkinson's disease patients and deep brain stimulation. And then a fact that a lot of people don't know about me is that I play the accordion.
Hi everyone, my name is Jing, and I'm a PhD student in civil engineering. Nearly my research area is about neural network and machine learning. So I want to take these courses to make a good foundation to take these courses, to take neural network and machine learning.
It will be useful.
Okay, I'm Jun Xian, and you can call me Joe. I came from Taiwan this summer, so I just finished my first semester. And actually, I'm not very good at signal and system stuff because back in my bachelor, I did very poorly. But before coming to the United States, I tried to review the material by myself, and hopefully I can more familiar with the topics because I think it's one of the hardest part in the EC majors.
Probably.
Hi everyone, my name is Ani. I have a bachelor's in industrial engineering from 7 years ago. And yeah, I worked in manufacturing roles for about 7 years and decided I didn't like it. And I found my passion doing a lot of electrical engineering work. So yeah, I decided to do my master's in electrical engineering, specifically with a focus on mechatronics, robotics, AI, that kind of thing. So.
Okay, great to meet you all. Okay, so what we'll learn in that course is mainly linear algebra-oriented numerical methods. You have multiple other courses which are teaching other things in engineering school, but in this course I will focus mainly on linear algebra because we have a lot of applications of it, and we will focus on systems of equations and linear system of equations, matrices, operations of different kinds. We will talk about linear spaces, which is basic linear algebra in a sense, but I will try to give to all of it different kind of applications, how you actually use it, and what is the intuition behind all of the things, because typically when you take that course from math department or from even engineering departments as undergrad, and most of the programs include some linear algebra at least in undergrad degree, they go through technique. They do not really go through meaning of what it all means, like why do you even need it for anything. And this gets you some sort of disconnect from the world of applications of linear algebra, because linear algebra has like tons of different applications. So we'll talk about eigenvalues, and these are two dominant problems in linear algebra. We're talking about systems of equations and solution for the systems of equations, and eigenvalue type of problems, and all of the related other problems which are connected to eigenvalue. And you have, again, tons of applications in multiple different engineering fields for eigenvalue problems. And we will see intuition behind it, what it means, why we need it, what we do with it, and so on. Then we will do also function fitting, all kind of least squares models, regression models, and you use it a lot in machine learning. You use it in multiple other domains as well, where you have a bunch of points, you record it from somewhere, and then you need to get some analytical function fitted to it, or some sort of curve passing through these points when there is no perfect fit. Typically, you don't have perfect fit because of the noise, and recordings are typically noisy, so you cannot really fit to all of the points. Otherwise, you'll be overfitting your function, okay? And we will talk about interpolation and extrapolation. So interpolation is when you actually want to pass through all of these points. So you want some curve, which is not between the points, close enough, but passing through all of these points because you want to approximate what happens between the points. So what you do, you feed the function to all of the available points. You know that they are correct. And then you want to fit points in between somehow. And since the function will be continuous, you can figure out all of the points in between based on that model. And different models clearly will give you different answers. So there is no like one correct interpolation way. You have multiple interpolations, multiple types of interpolation, and different kinds will give you different advantages and disadvantages. And I think that most important part of that course for you to understand is to value these advantages and disadvantages to make concise choice of which way you want to go with it, like what technique you want to use. Because if you don't understand the assumptions of the technique, then you're just choosing it randomly and your results might not be correct results or good results. Okay, again, we cannot even talk about correct results here because there is no ground truth to have correct results. But results which make more sense to your particular field based on your assumptions on what you know about the field. Okay? And extrapolation is practically trying to predict what will happen to these points if you move on to the places where you haven't measured them. So that's what extrapolation is. It's like how this function is continuing after you have no data points anymore. So these are the things in linear algebra. We also will think about numerical implementations of derivatives, integrals, and this connects us to all of this particle filtering, computation of integrals, practically numerical computation of derivatives and numerical computations of integrals. We will not go too deep in that, but we will have some portion of it devoted to these things, okay? How about solving nonlinear equations? So we might have nonlinear equations, which we also need to find roots or derivatives or some other things, and we can do that numerically. Typically, you cannot solve systems of nonlinear equations analytically, not many at least. Most of them you cannot solve. So you solve them numerically, and you have multiple different methods to solve these nonlinear equations somehow using numerical methods. And for that, you're using a little bit of calculus. And then we will talk, hopefully at the end, a little bit about optimization techniques, because a lot of machine learning, controls, and other areas have a lot of optimization in it. It's like how you minimize something or maximize something, okay, numerically. When the functions that you want to minimize and maximize is too complicated to do that analytically. Because if you can compute simple derivative of a function, that's fine. You can just compute derivative. Derivative 0 will give you maximum or minimum. This is Fermat theorem, that at minima and maxima you have 0 derivative, right? But if function is more complicated, then especially if it is given to you numerically, you cannot compute really derivatives and find that place of maxima and minima. Okay, so motivation for this course is very simple because matrices used almost anywhere. They used to describe linear equations, systems of different equations. And with matrices, which is maybe more surprising to some people, you can describe derivatives, all kinds of transforms, integral transforms, for example, like Fourier transform, Laplace transform, and many other transforms. Convolution, which is practically basics of filtering, right? It's convolution operation, which is also integral. So you can compute all of that using just matrices. You don't need to compute integrals. You don't need to compute anything else. So in discrete space, you're just using matrices for that. You're multiplying by matrix, you get DFT transform. This is how it works. And if you want to find inverse DFT transform, you multiply by inverse matrix, same matrix, obviously, okay? And it gives you inverse DFT transform, which is nice to have, right? Also, linear algebra has tons of different applications here. And these applications include computer vision. You have a lot of it because practically speaking, image is a matrix. It's just a bunch of numbers in a table. This is what matrix is. And this is what image is. Technically speaking, color image is tensor, not exactly matrix, but gray level image is matrix, okay? It's like 2D. You don't have RGB, red, green, blue type of layers in gray level image, so it's just regular matrix. You have a lot of matrices in control systems, everything which is related to state space analysis and so on. It's all based on matrices. You have machine learning. Machine learning also has a lot of linear components in it and solving tons of linear equations. sparse matrices, regular matrices. All the neural networks are based on matrices. You have also nonlinear components to that, like activation function, for example, in neural network, but most of it is just basic linear combination of inputs, which is getting us to linear algebra back. All right, and then you have all of the data science, which is analyzing tables of numbers of some kind. And tables of numbers are matrices or vectors, depends on how you look at it. So it's all kind of interconnected and connected to linear algebra. So tools which are used in all of these disciplines are almost the same tools, very similar. All right, a few quotes which are describing my philosophy in that course. So raise your hand if you heard the name Johnny von Neumann. Okay, this is actually a very famous person, and we know him for multiple different things, including Manhattan Project, which is atomic bomb project, but the main thing that we are using practically every day is computers. He is, practically speaking, theoretical father of computers. He invented that architecture, which we still use, von Neumann architecture of all modern computers, digital computers. Before that, they had analog computers, which was kind of computing different things as analog voltage was changing as the output of that computer. He invented architecture with memory, connected to ALU, arithmetic logic unit, and all of that structure which is used in microprocessors now. Okay, so he was that famous physicist, mathematician, and so on, polymath. And he had a lot of different ideas, and you can find many funny stories about him, that he was computing things faster than computers in his head. He was like genius that even other geniuses considered him genius, okay, compared to themselves. He was really genius. He would be computing like triple integrals in his head in a second, like that. He was just able to do that. And this is why he has like a lot of jokes on his name, and he was kind of funny, weird person in his life. Because of that kind of computational abilities that he could compute different things like dividing, like in high school, he was dividing 8-digit numbers one by another in his head, like that, you know, before calculators, okay? This is before calculators in probably like 20s or something, 100 years ago. Okay, so his opinion about math. This is very important to understand where I'm going with that, okay? So these two quotes. In mathematics, you don't understand things, you just get used to them. This is very important to understand what it means, okay? Many things, people typically don't really like math because they don't have that background to build that block on top of another block, and then to build that entire picture. And since they do not see the entire picture, it's very difficult for them like to learn new thing, because you're building that new thing on the air and you don't have that fundamental stuff below. So it just falls apart. You cannot really learn it. So technically, you can build that fundamental stuff first, then the second layer, third layer, and learn all of that building, okay, of math, which is huge, beautiful, if you get it, okay? It requires years of training. If you miss something, you don't have these years of training, okay? So forget it, it will not work that way. You don't have time to spend on it. So some of these parts you will just have to accept on faith in a sense, because people prove different theorems, develop different things in math, and you just don't have time to understand all of the details of how they developed all of that stuff, okay? You just don't have time physically. It's impossible to get all of that. So the point of that quote is that you shouldn't be distracted by that, and you shouldn't be disappointed in yourself, and you should kind of say that, well, I'm not good for math, I'm not ready, I'm not having that background. Try to get it as you learn languages. Just pick it from the point you start. and accept it as is, try to implement it. You might learn it later how you got there, okay, to that particular piece. So it's important that you will start from particular point. You don't have to understand everything. Just use it and get used to it, okay? Then it will become your second nature if you're using it enough. For you, it will be like, oh, obviously, this is how it works, okay? It just naturally will come to you if you have that habit of using these things. So that's one thing. Second thing, if people do not believe that mathematics is simple, it is only because they do not realize how complicated life is, okay? So our mathematical models, you will always remember that's just simplistic model of life. It's not real life. So if your mathematical model tells you something, it's just not precise description of what life is and what you actually want to do with it, okay? It just gives you basic idea or can push you into some interesting direction with it, okay? But it's not real in a sense. So physics is more real than math in that sense. Okay, we will see multiple different applications in that course. I hope that I will be able to go through all of them, or maybe even more. We'll see how it goes. Like k-means clustering, which is part of computer, part of the machine learning processes. Clustering is unsupervised machine learning. Then we will talk about neural spikes. If you're interested in neuroengineering, how to sort different neural spikes. Image segmentation type of problems, how you segment different parts of the image and describe their contours or centroid or other things. How you compute electrical circuits, so it's more related to electrical engineering. Typically, it takes probably like half a semester to learn how you compute currents and voltages in different points of the circuit with all kinds of resistors, batteries, capacitors, and so on. You don't need any of it. You have technique which with linear algebra allows you to learn all of that in probably like 10 minutes. So I don't understand why people learn linear algebra after circuits, because if they would learn it before circuits, half of the circuits you can throw out, you don't need it. You can just put matrices, invert matrices, and get all of the voltages and currents at the same time. You don't need to worry about that part. Okay, spectral analysis, which is very important, like to see what is the distribution of different kind of frequencies in your signal. This is part of signal analysis. Most of the disciplines using some kind of filtering or pre-filtering before they analyze any signals or control any signals. We will talk about optimization methods like stochastic gradient descent, very important for machine learning as well. Simplex optimization methods, then principal component analysis, which is reduction of dimensionality. If you have too many variables, you want to use only important variables. Like how would you know which ones to use and how you deal with that? Compressed sensing, which is, if you know a little bit about signal processing, you probably heard about Nyquist-Shannon theorem, sampling theorem. And the theorem states that if your signal is sampled at particular frequency, okay, at particular sampling rate, you cannot reconstruct that signal unless the signal does not include any frequencies above Nyquist frequency. Okay, and Nyquist frequency is half of the sampling frequency. So if you have any fast ripples in your signal, you cannot really reconstruct it from sampled points if you're not sampling fast enough. This is the overall theory. But if it is very slow signal, like not fast ripples of some kind, then you can reconstruct it exactly using sinc functions. It's like sine x divided by x functions. These are base functions with which you can reconstruct exactly the original continuous signal from points. So you have that condition. But people came up with question like, can we reconstruct other signals with faster ripples, but we will not sample them with equal sampling rate, but with more adjusted and adaptive rates. So we will sample it maybe more points where it's fast and less points where it's slow. So we'll have exactly the same number of points, sampled points, but we'll be able to reconstruct higher frequencies somehow. It's kind of smart sampling. So this is that compressed sensing type of sampling idea where you can take not every point, but maybe particular points at particular times based on how signal looks like in time, and then you will sample it in particular way, and you will store only particular points instead of like doing that on the clock. neural networks is fun area which is now applicable, I believe, in all possible applications. I cannot even think about any applications where you don't have any artificial intelligence anymore. Dynamical systems, their stability, again, state-space systems, transfer functions, and all of that includes a lot of the stuff that we will be learning here. Eigenfaces, it's to demonstrate how you can recognize different faces or build any kind of faces with limited library of other faces. Like how can you combine multiple pictures of faces to generate new faces, which is fun area. It was before neural networks. People invented that for recognizing faces or for simulating new faces from other faces. So you have some theory related to eigenvalues in these eigenfaces, okay? Life hacks. Okay, so what we will not learn in this course, okay? We will definitely not learn much about partial differential equations. If you need partial differential equations, you can find 2 or 3 other courses in engineering which are teaching numerical methods for partial differential equations. In mechanical engineering, probably civil engineering, BME, all of these departments giving a lot of emphasis in their numerical analysis to partial differential equations. I do not feel that we have a lot of need for solving partial differential equations, so it's not my field as well. And we will also not learn finite element methods, which are very popular in fluid dynamics and other applications. They are very important, but not in our areas. Typically, we do not use FEM for what we need. And I will not also go into deep analysis of optimization techniques because you have so many of them. All of them are very interesting, but you need separate course for that, for learning optimization, okay? I will just touch a few basic things, just ideas from optimization. Now, regarding syllabus, so what are our objectives in that course? First of all, I want you to be able to learn terminology and understand scientific papers which are using that engineering and mathematical terminology. And this is why the first probably few lectures will be kind of boring, because I will be talking about nomenclature mostly, like symbols, sets, symbolics, which means it's not like real stuff in math. You just need to understand the language of theory of sets because people are using that all the time in all of the engineering papers. Okay, so you just need to know the language. And at the beginning, it's always difficult to learn the language, right? So it takes some time until you get used to it. Again, coming back to that philosophy, like you just need to get used to it. It will be hurting at the beginning, okay? But you'll be fine later. You will use it, and as time goes, you will just say like, yeah, sure, I know that symbol. Like I understand it now, okay? After you use it 10 times. So I want you just to be able to read all of these papers and to understand what the symbols mean. Now, second thing that I want you to do is to build that intuition behind linear algebra theorems and approaches and methods and calculus as well. Because it's very important to understand background and to see assumptions behind all of these theorems. If you do not take assumptions into account, you might do wrong thing. You will assume something which is wrong, and then you apply something which should not be applied in particular circumstances. So it's not a good idea, okay? You just getting some random result. Now, applying numerical methods using computer programming. We are doing numerical methods, you will have to do some programming. Is there anyone who has no experience in programming of any kind? Okay, so you will have probably to take some sort of crash course on how to program stuff. And MATLAB is the easiest one because you have interactive courses online, MATLAB Academy, where you have MATLAB on-ramp or signals on-ramp, and you have multiple different things. It's free for all UB students. You need to install MATLAB version to download it from the website. So you'll have to register, like all of you can, if you don't have MATLAB yet, you can register with your UB account. It will be free for you to download recent version of MATLAB, to install it on your laptop. it will be easier to go through examples, through homeworks, and so on. And you can install that updated version, and you have MATLAB on-ramp and other courses which are in MATLAB Academy. They have a website which is called MATLAB Academy, where you have interactive lectures. It asks you to do some tasks, you write some code, it checks the code automatically and says like how to improve it. Okay, so you have all of these learning abilities. I think it's like not more than half an hour for learning basics of MATLAB, and then probably a few more hours to learn more advanced stuff in programming if you need to refresh your memory on how to do that. Okay, and we will not go in that course like very deep in programming. We will not do any like real deep programming assignments. Mostly we will be dealing with using some sort of libraries or some basic applications, a few lines of code, just to see how stuff works. Okay, and I picked MATLAB specifically for two reasons. One, because I know it better than other languages, and which is obvious reason. And second one, MATLAB is the closest one to theory, which means you define matrix as you almost defining it in mathematics. Okay, so math very similar to MATLAB in that sense, symbolically. And also you will need to do some self-learning, and it's always good to have skill. And we will do presentations in class. At the end of the class, we will have project with presentations, so you will have also experience presenting that to class. I don't know how much time we will have left for presentations, so potentially I'm considering that maybe we could record your presentation and then to have it like presented online somehow, if we need to save some time, but we will see how it goes, okay? This is why I need feedback from you, like, are you okay? Are you still following what we are learning? And this is the main quote for this course. And I took it from very famous textbook on numerical methods by Hamming. Have you heard about Hamming? So electrical engineers might have heard like Hamming codes and other stuff like that. He was also a famous engineer and mathematician, invented multiple different things in digital communications, numerical methods, and so on. So his quote is saying that the purpose of any computing is insight, not numbers. This is where we are trying to get. I will not like sit with you and solve questions just to show you technique. Technique is important, that you will do things the right way, but this is not the meaning of it. It's not the important thing, okay? The important thing, just let me check something, okay. The important thing is what kind of insight you get out of it. What is the meaning? You get some bunch of numbers. What is the meaning of these numbers? Sometimes people just put them on paper saying like, this is the result that I received, without thinking if it makes any sense. It's important that numbers will make sense. Otherwise, your computation doesn't matter how well you computed stuff if numbers make no sense. All right, we're looking for sense to numbers. I don't have any required textbook. I don't think that single textbook can cover things that we need to cover. But there are multiple different textbooks which are very interesting, good quality textbooks that I would recommend just reading if you are interested to develop some sort of algorithms or some numerical methods in the future. So this is the, no, you cannot actually see my mouse. I will point like that. So this is a textbook by Hamming that I was talking about. This quote is coming from that textbook. Okay, so this textbook is very important by Golub and Van Loon. And this book is important because almost anything related to numerical analysis, related to linear algebra, if you see any citation, it's citation to that book. This is Bible of numerical analysis. Okay, it includes almost any possible technique which you can do with matrices. This is like the book. So if people say like, oh, I use that numerical technique, citation, that book. This is the book to cite for any of your papers because it includes all of the matrices techniques, all of them. Okay, it's like a book like that, like big book. Okay, now the book below it, this one, is the smallest book on numerical analysis, that kind of book. Okay, And it includes partial differential equations and numerical methods and calculus and linear algebra and like all of it. And it's pretty accessible. It's not super dense somehow. They don't have many examples in it, but it's pretty understandable. It's good to learn all kind of, especially calculus, if you're interested also in differential equations. This is the book to read. I don't know, maybe like 50 pages or something, 70 pages. Relatively small book, okay? Well-written book. Now, as I said, this Hamming book is a classical book. It has tons of different methods, especially nonlinear equation solution numerically for these equations and so on. This book includes a lot of MATLAB examples and has practically codes for all of the algorithms that you would be ever implementing in numerical methods. Okay, so it has all of the computational examples with theory. So it's a pretty good book. Now, I like this book because it connects everything to machine learning. So if you're interested in machine learning and data science, this is one of the best books in that direction. And Gil Strang, he is very famous for his online linear algebra lectures, video lectures, probably the most famous video lectures from MIT. He relatively recently retired from MIT, and he was teaching linear algebra for probably like 50 years or more, maybe 60 more years. And he developed his own technique explaining things. Very clear technique. He is explaining things by example, from very basics to very advanced stuff, including engineering math and the Kalman filters and other stuff like that. Okay, so I strongly recommend going through his video lectures, and this is one of his textbooks related to machine learning and linear algebra numerical methods. All right, and these two books are available online for free, so you can just download PDF for free for both of these books, and they include a lot of topics from what I plan to teach in that course. All right, so you have links here which show you where to download these books. They are also, this book is probably a little bit more advanced, and this book is a little bit more basic. Though this was written for Stanford students, so I'm not sure if I should call it basic. Not very basic, okay, but it like goes from elementary vectors and to matrices and to all of the basic stuff. So it gives you enough background to understand all of the advanced stuff that they get a little bit later. Okay, any questions so far? Okay, so here is how I plan to have grading. So as I said, attendance is important more to me than maybe to you, but I think it's also important to you because in class interactions, when you especially teaching math, it's very important to see what level I need to go that will be more or less understandable by at least most of the students. And then I need your feedback to see if it is. We'll have homework, which is dry, like writing, solving open questions of some kind. I don't think that we'll have them every week, but maybe like once in a few weeks, some assignment that you need to write something. We'll have MATLAB or other language labs, okay, where you need to write some code. It will not be like too difficult. It's just you're going through the steps, you're implementing something, you see the answer, you're playing with numbers, seeing how different things are changing, and so on. And we will have project which will take 40% of the grade. So this project will be, it's better to start the project as early as you can. So you can come up with some idea where you need some numerical implementation of something. And you can talk to me, and then we will decide what we do with that. Or you can ask me if you want to, that I will pick some project for you. All right, so again, I discussed most of that. Maybe, I'm not sure about finding an evaluation of materials. It's practically useful that you will learn by searching different things and reading different things. So I'm considering if I should include that as part of the homework. It will be just your free time type of thing, that you're just doing that for yourself. And I don't really need to grade it in any sense. It's just kind of useful. And another thing that I'm considering if I should do is to give you to design some of the project problems for future use in that course. Because again, I want to convert that course into online. And when I'm converting that course into online, I want many questions to be available in question banks for quizzes, for all kinds of questions that I can just pick from multiple questions to ask different semesters different questions, for example. So we need to design new questions. And I think the ability to design questions is interesting ability in itself for you to learn, okay? Not only answering questions, but also asking questions in such a way that it will be very clearly formulated. So clear formulation of a question is talent of some kind, okay? So you need to train that type of talent in yourself because it will be useful in your life as well, okay? Now, again, if you think that this is a bad idea and you want like more time, we can talk about that. I will put some deadlines on the homeworks because I also will need to actually check them and grade them. So if you push them all to the end of the semester, it will be a nightmare for me to check them all at the same time. And you also want probably feedback at the time when you submit them, so we'll have some deadlines for that. For MATLAB-based labs, all of the examples will be in MATLAB that I'm giving in the lectures, but you can use any other language if you want, as far as all of the results are correct. Okay, this is the point. And I also have some deadlines for them, but we will talk about that. And project will include, as I said, some implementation of some project, maybe something that you research, maybe related project, or something that we can pick out of different topics that you are interested in, or I'm interested in. So we can talk about that. You will get my approval to start the project, to work on it through the semester. And then at the end, you will have presentation on that project. And I think that report should look like a paper, short paper, scientific paper. So you will have also some sort of training on writing scientific papers. If you invent something new, you can publish it, which is additional benefit from it. But this is how I envision that to run. Now, usage of AI. This is a new thing that people typically include in courses. People tried to fight calculators when they came out for a long time. They said like prohibiting calculators in the classroom. Do not use calculators in your homework. Then do not bring it to test. Then waste of time. Use AI, okay? AI is new important tool. You can learn from it. But do not put yourself at disadvantage by using AI. When you use AI, try to learn from it. And before you use AI, try to solve your problems by yourself, for yourself, okay? It's just you need to develop your mind, and AI can help you with that, but if you just believe AI as is, it will not help to develop your brain anyhow, right? So you want to learn from it, and you can. So use it, whatever you want. Same thing if you want to check some numerical answers, use MATLAB or whatever other tool to check your answers. That's fine, okay? Because at home you will have it. Like at your work you will have it. Like why, I shouldn't prohibit it. It's silly to prohibit that kind of thing, all right? Use whatever tools you can find. Just take responsibility for your answers and document it. Say, I used it in such and such way. This is legal, correct way of using AI. You're just stating it, and it's completely fine. Okay, if you are stating it. If you have any kind of special needs, special circumstances, anything that I need to know about regarding you coming to class or not coming to class, health issues, whatever it is that I need to know about, that you will not be able to be here at particular days sometimes, let me know ahead of time. Again, if you have some emergency, obviously you cannot let me know ahead of time, but otherwise try to let me know, okay? Yes?
Would you upload the PowerPoint to the Canvas?
Yes, I will upload PowerPoint to the Canvas, yes. But as you can see, we will write something on the board and other things, so it might be tricky to upload all of these parts, and technology might fail us So PowerPoints, yes, will be on the cloud. And I'm thinking to record even the entire video, like Zoom and voice over and all of that. But again, I don't know how well it will work here. We'll see. So prerequisites that I do not expect but would be nice to have. Obviously, some algebra and linear algebra basics, that you know what matrices are. You can learn it through that course, but it would be nice that you see that second time and not the first time. Matrices, right? It's kind of easier. If not, just let me know. I will try to provide some additional background material on linear algebra, for example, or quadratic equations. I don't know, whatever background you need on algebra. Calculus, also, I do not expect you to solve triple integrals. You just need to know what derivative is and what integral is. Like, it should not be completely new thing to you. We will go through that. I will explain intuition behind it. But again, it's nicer to see that already second time and not first time. And we will not solve analytical integrals of any kind. It's just, you just need to understand what it means. These are the topics that I plan for this course. We will have all of the linear algebra topics first. Vectors, matrices, determinants, linear spaces, eigenvalues, SVD, with all of the numerical implementations and applications of it. Positive definite matrices, which is very relevant for stability and controls and other places like that. Interpolation, extrapolation, function fitting, special matrices. This is like DFT matrices, for example. And then calculus side will be about derivatives, finding equation roots, integrals, Monte Carlo methods, which is that particle filtering stuff, and some optimization techniques. Okay, so this is overall list of topics that I hope to cover in this course. And this is about syllabus. Do you have any questions, requests, concerns? Yes?
When you say programming labs, are they like we're in class working? Like
No,
you, or-
at home. It's assignment, home assignment, yes. Yes.
The project is individual, right?
Interesting question.
Yeah, because I saw group project on.
Probably group project. I don't know, like how many projects we'll be able to present in class. So I'm planning, we have like 12 people probably registered to that class. So if you're doing that by pairs, it's already 6 projects, and you need to present it, and each presentation will take like half an hour, right, approximately. So it's like you need already 1 week for 4 presentations, so it will take already like 2 weeks, which is, but if it is individual, it's like half a semester to present it, right? So we can do individual ones where you're presenting maybe online, like recording yourself, like with webcam or and PowerPoint or something like that, or doing in pairs and then presenting in class. So I prefer presenting in class because you get audience questions. Because for online video, you cannot get really audience questions. And you don't have also that interaction talking to people as you present. So I prefer that experience in class. So we probably will allocate like 1.5, 2 weeks for that experience in class, and it will be in pairs, like 2 students per project, something like that. This is how I see it. But if you want to do that individually, I think it's possible if you prefer that way.
Yeah, no, I prefer group because, like you said, like it would take much too long to have all the.
Yeah, so it's like technical issue in a sense.
Yeah.
Like individual, I mean, maybe you will learn more because sometimes in pairs, like the division of work is not even, so you learn half of it, and it's always better to know all of it. So, but still, we will do that in pairs, yeah. Any other questions? Yes.
2 questions. One is that if I would like to review the linear algebra,
Mm-hmm.
would you suggest me to do? And the second question is how to find the ideas of the project.
Okay, so about ideas for projects, you can come to me and we can talk about multiple different, I have probably like 50 different projects that could run through some sort of numerical analysis techniques. So this is not an issue, but I don't know what you're interested in that much. So you need to tell me first what you're interested in, and then I will try to figure out what is the best match to what you need in your future development of career. Now, for linear algebra, basics of linear algebra, you have multiple different possibilities how you can learn linear algebra relatively fast. You have video lectures, which are summarizing all of the important topics from linear algebra on YouTube, or OCW from MIT, like Gil Strang lectures online. But they still will take you some time to learn, right? So these are like full lectures on linear algebra. And you don't need all of the topics. All you need is practically only a few subtopics, which are the most essential topics for that course, which are understanding what vectors are, what matrices are, eigenvalues, and solving systems of linear equations. That's it, basically. These are the basics of linear algebra. You don't need to go too far into like linear spaces or all of that stuff, which is more advanced. We will learn all of that here. I will go through the important parts of the things because eventually this will become very important for signal analysis, especially, and machine learning, all of the spaces, more abstract type of thing. But we'll go through that, so you don't really need to go there. For matrices, you still, I mean, I expect you to know something about it. This is a rectangular table of numbers, and then you can multiply it by vector. And again, I will go through all of it, so I will not assume any background. But my experience with linear algebra is that you need some repetition, multiple repetitions until you get it. Like when I learned linear algebra as undergrad, it took me time just to get it because it was too abstract for me. All of this like rules, you're multiplying row by column and then like element by like, and then you need to remember all of these rules, and then you're overwhelmed with like why you like multiplying from left, and then you cannot switch matrices, and you know all of that stuff. So it starts to be like overwhelming when you are learning that first time. But when you see that second time, it was almost like, well, I used to that already. I get it. Like I will not switch order of matrices anymore because I know you can't. It will be different, right? So you get used to that. So to get used to that, you need some experience. And this is why I hope that you have already some exposure to the things, and you computed by hand some matrices multiplied by some other matrices before, and this will be not the first exposure to that kind of thing, though I will do it, okay, anyways, here, all right? Yes?
We have to bring laptops to class.
Laptops, you don't have to. I would prefer that you will bring pen and paper because, unless you can type fast formulas, because I will be writing probably some stuff on board. I think the best examples that I can provide are better written and described on board with handwriting because it combines graphics with formulas with text. And like electronic thing, I don't want to show that as presentation slide because you will not get it. It's like order is important, thinking time is important, and the time which takes me to write that stuff is the exact time which can take you to copy and understand that stuff. So if I go too fast, you will not get it. So it's a waste of time. All right? Any other questions? All right, thank you.